Welcome grade 12s to STEM in Action's Boost series. I'm V Guyan, and today we're going to have a look at acids and bases. Some pre-knowledge you should know from grade 10 and 11. What are aqueous solutions and how do substances dissolve in water? Our basic acids and bases examples. How to balance chemical equations. Quantitative aspects of chemical change, those are our calculations such as percentage purity and percentage yield. Right, so what are acids and bases? We can learn all the formal definitions, but we actually have some acids and bases in our home. So we're going to have a look at some of these acids and bases and test whether they are acids or bases. So you can see here, I've got some vinegar, I've got lemon juice, I've got a cup of coffee, I've got vanish, then I've got some handy Andy, and I've got glass and surface cleaner, Mr. Sheen. And so we're then going to spray or drop a little bit of each substance onto our red and blue litmus paper here in front and see what happens, and then decide if they are acidic or basic. Let's have a look. We'll start with the coffee, and we're going to drop it onto our litmus paper. And so if we have a look there, we can see that the blue litmus has gone a little bit red, not very dark red. The red litmus has definitely stayed red, so we can see that has a slight acidic properties. Let's have a look at our vanish. Okay. Oops. Okay, so we can see our red litmus has definitely gone blue, our blue litmus has stayed blue, so therefore our vanish is a base. Right, so we'll have another look, we'll have a look at some lemon juice, and I'll just drop some into here. And we can clearly see our blue litmus went red, and so therefore our lemon juice is an acid. We'll just swiftly move on to the next one. I've got some handy Andy here. I'll pour some handy Andy over. Right, so let's have a look. Oh, we can definitely see our red litmus has turned blue, and so handy Andy is also a base. Moving on to our vinegar. Very clearly, vinegar over here, we've got our blue litmus turning red, our red litmus stayed red, and so that is an acid. And the last one we're going to have a look at is our glass multi-surface cleaner. And so we'll just spray onto the last one there. And that is also acidic. We can see that the blue has slightly got a bit of a red color, not a very strong acid, but it does have a little bit of a reddy color to it there. And so out of our samples here, we had quite a few acids. We had vinegar, our glass and surface cleaner, our lemon juice, and our coffee were all acids, and then our vanish and our handy Andy were both bases. So we can see that in our households, in our everyday dealings, we are dealing with acids and bases. So when we talk about acids and bases, we all have ideas of what an acid is or a base is. But there was a scientist, Arrhenius, who came up with his own theory. And he said that an acid is a substance that produces hydrogen ions in water. He said that a base produces hydroxide ions in water. However, this definition was a little bit limited because not all bases produce hydroxides in water. And so Laurie Bronsted, who are two scientists, they came up with their own theory. And they said that an acid is a proton donor and a base is a proton acceptor. So an acid being a proton donor, where do we get a proton? Remember, we'll often refer to a proton as H+. Why? Because hydrogen has just one proton and one electron. And so if it loses that electron, it becomes H+. It's simply a proton. And so if we have a look at something like HCl, it has hydrogen, and so if it can donate that H+ to something else, then it is an acid. Whereas a base is a proton acceptor, so it will accept that H+ from an acid if it is a base. Right, let's have a look at an application question from November 2018, question 7.1.1. Question 7.1.1 says, define an acid in terms of the Laurie-Bronsted theory. So the Laurie-Bronsted theory said an acid is a proton donor. And there we have it. Let's carry on to the next part of acids and bases. In grade 10, we learned about aqueous solutions. Aqueous solutions are when substances dissolve in water. This happens in a number of ways. The first being ionization. Ionization is when the substance actually reacts with the water to form ions. For example, HCl. The HCl will donate a proton to the water and we'll get a hydronium ion. The hydronium ion is H3O+. And what's left then from the acid is our Cl- ion, our chloride ion. Similarly, with ammonia, it will also react with the water to form ions. In that case, ammonia is a base, so it's a proton acceptor. And so water donates a proton to the ammonia, and we get the ammonium ion, the NH4+ ion. And we also get the hydroxide ion from the water. On the other hand, most bases actually undergo dissociation, and that is where they simply break up into the ions, and the water is not required in order to form the ions. It happens in water, but the water is not a part of the forming the ions. And so NaOH, sodium hydroxide, simply breaks up into the sodium ion and the hydroxide ion. So let's talk about strong acids versus weak acids. A strong acid ionizes completely in water to form a high concentration of hydronium ions. Examples of strong acids: hydrochloric acid, sulfuric acid, nitric acid. Our weak acids ionize incompletely in water to form a low concentration of hydronium ions. And examples of weak acids are ethanoic acid or oxalic acid. We know from chemical equilibrium that our Kc values are equal to the concentration of our products over the concentration of our reactants. We can do a similar thing for acids, and then we particularly call it the Ka value, the equilibrium constant for an acid. If we have a high Ka value, it indicates it's a strong acid. Why is this? Because for strong acids, they ionize completely, which means our equation lies far over to the right. We have a high concentration of products and a very low concentration of reactants, and therefore we're going to get a high Ka value. On the other hand, for our weak acids, our equilibrium is going to lie much more to the left, to the reactant side of the equation. This means that there are more reactants than products. The concentration of the reactants is higher than the concentration of the products, and so we get a low Ka value. To give you an idea, some of our strong acids and weak acids are listed in the table you see in front of you. Notice that there are 6 strong acids listed. We normally talk about the 3 that are highlighted there, hydrochloric, sulfuric, and nitric acids, but also perchloric, hydroiodic, and hydrobromic acid are also all strong acids, and in fact stronger than the 3 we are used to seeing. What we must point out is that the Ka values for all those acids are greater than 1, which tells us that the concentration of the products is greater than the concentration of the reactants. On the other hand, if we look at the weak acids down at the bottom, There are just a few examples that have been given in the table, and all of those you can see that the Ka values are less than 1. And so they are weak acids. The concentration of the reactants is higher than the concentration of the products. Let's have a look at an application question from November 2019. Question 7 says, a hydrogen bromide solution, HBr, reacts with water according to the following balanced equation. And there they give you the equation. The Ka value of HBr at 25 degrees Celsius is 1 times 10 to the 9. Question 7.1 says, is hydrogen bromide a strong acid or a weak acid? Give a reason for the answer. Well, remember that when we talk about a strong acid or a weak acid, we know that Ka is directly related to that. And we just learned that if the Ka is greater than 1, it is a strong acid. So if we have a look, it is 1 times 10 to the 9, which is definitely greater than 1, and therefore it is a strong acid. So 7.1 is a strong acid, and the reason Ka is greater than 1. So we spoke about strong acids versus weak acids. Let's talk about strong bases versus weak bases. Firstly, the definition. A strong base dissociates completely in water to form a high concentration of hydroxide ions. Notice when we spoke about acids, we spoke about ionizing, and with strong bases, we speak about dissociation. Examples of strong bases, sodium hydroxide and potassium hydroxide. Our weak bases dissociate or ionize, depending on the base, incompletely to form a low concentration of hydroxide ions. Some examples, ammonia, calcium carbonate, potassium carbonate, and sodium hydrogen carbonate. So let's talk more about the strengths of the bases. Again, we can talk about our Kc value, or when it's particular for bases, we'll call it a Kb value, the equilibrium constant for dissociation of a base. So a high Kb value tells us that it is going to be a strong base. Why is that? In a strong base, we know that it dissociates completely to form a high concentration of hydroxide ions, which means that our equilibrium lies far to the right. On the other hand, a weak base is going to have a low Kb value because our equilibrium lies far to the left. And so we have a high concentration of reactants and a smaller concentration of products. Again, we can have a look at a table of strong bases versus weak bases. Our strong bases are generally our group 1 and 2 hydroxides, and they are all going to have a Kb value of greater than 1. Where our weak bases are carbonates, other hydroxides, and ammonia, and they all have a Kb value of less than 1. While we're talking about equilibrium constants, let's talk about the equilibrium constant for water, or Kw. Water can undergo autoionization. This means it reacts with itself to form ions. Now you may see the formula given like that with water plus water, but more often they'll actually simplify it to just say there are 2 water molecules and they're reacting together. Our Kw then is going to simply equal the concentration of the hydronium ion multiplied by the concentration of the hydroxide ion. Because water is a liquid, we don't put it into the Kc expression. At 25 degrees Celsius, we find that the Kw value is always 1 times 10 to the negative 14, which means that if we have the concentration of the hydronium ion or the hydroxide ion, we can find the concentration of the other based on that equation. Also, if we are finding the equilibrium constant for water, we know that the concentration of hydronium ions will equal the concentration of the hydroxide ions, which equals to 1 times 10 to the negative 7. Let's talk about pH. The pH scale is something that you have been exposed to since the younger grades, and it is still relevant with acids and bases even now in matric. We know that the pH scale is a scale of numbers from 0 to 14, which is used to express the hydrogen ion concentration. And so we can get the formula that pH is equal to negative log of the concentration of the hydrogen ion or the hydrogen ion. You'll often find that these two are interchanged. This is because you won't simply find a proton hanging out by itself. And so the hydrogen ion, which is simply one proton, will be attracted to the water molecule and to the lone pair of electrons on the oxygen side of the water molecule. Let's have a look at a multiple choice question from the November 2019 paper, question 1.7. Question 1.7 says a hydrochloric acid solution, HCl, and acetic acid solution of equal concentrations are compared. How do the H3O plus, the hydronium ion concentration of HCl, and the pH of HCl compare to that of the acetic acid? Right, so we know that HCl is a strong acid and acetic acid is a weak acid. The strong acid produces a high concentration of hydronium ions, and a strong acid on the pH scale, we know that's on the lower end of the scale. So we go and we have a look at our table. And so we first look at our concentration of hydronium ions. We know for HCl that should be higher, and so we're looking at either A or B. And then our pH acids have a low pH, and with hydrochloric acid being a stronger acid, it should have a lower pH than acetic acid. And so our answer would be B. Right, let's have a look at another application question. We'll have a look at November 2018, paper 2, question 7.3.1. Question 7.3 says the water in a certain lake has a pH of 5. Calculate the concentration of the hydronium ions in the water. Okay. So we know that pH is equal to negative log of the hydronium ions. They've told us the pH is 5, and they want to know what the concentration of the hydronium ions are. The first thing first, I'm going to take this negative across, so I'm going to have negative 5 is equal to log of H3O plus. And then to get rid of the log, we know that logs have a base 10, and so we take that base 10 across, it becomes the base on this side, and the negative 5 gets pushed up to the power. So it becomes 10 to the power of negative 5 is equal to the concentration of the hydronium ion, which we can then just write as H3O plus is equal to, we don't like to just write 10 to the negative 5, so we say 1 times 10 to the negative 5, because 1 times anything, still 1. So 1 times 10 to the negative 5. What are our units for concentration? Moles per decimeter cubed. So the next thing we need to talk about is monoprotic versus diprotic acids. A monoprotic acid is one that can only donate one hydrogen. So if we look at something like HCl, it has one hydrogen, so it can donate one proton. However, a diprotic acid has two hydrogens, such as sulfuric acid, H2SO4. And so it can donate two hydrogen ions, and therefore is called diprotic. We've looked at a number of ways to compare the strength of acids and bases. To summarize, we can look at the pH, and in there we've also got to look at monoprotic versus diprotic acids. We can also look at the conductivity of acids or bases, and we can look at the reaction rate for acids and bases. Let's have a look at some demonstrations of these now. Now we're going to have a look at how the strength of an acid affects its reactivity. Remember that we said that a strong acid ionizes completely, and so there should be more ions in solution than a weak acid, and so therefore we should see more reactivity for a strong acid than a weak acid. So what I've got here in front of me is I've got a beaker with sulfuric acid, and I've got one with acetic acid, and we are going to add a little bit of magnesium ribbon to our two solutions and see how they react. So I'm just going to take off a little piece. We'll make the two pieces of magnesium more or less the same size. Both of our acids have a concentration of 1 mole per decimeter cubed. And so the only difference between the two really is the strength of the acid. I'm just folding my magnesium up. So I've got my two little pieces. Let's go ahead and have a look at what happens when I add them to the two solutions. So we can immediately see that the sulfuric acid, there are a lot of bubbles forming. And if you look closely at the acetic acid, there are also some bubbles forming there, but not as rapidly as our sulfuric acid. And so we can clearly see that sulfuric acid has a higher reactivity than the acetic acid. In grade 10, we learned about aqueous solutions and their conductivity, and we learned that the more ions there are in solution, the higher the conductivity. So we can also look at conductivity as a measure of the strengths of acids or bases. In front of me, I've got a beaker with some ammonia, and then I've got a beaker with sodium hydroxide. I also have a conductivity sensor here, which is linked up to our laptop, which will then measure the conductivity of each of these solutions so we can see which one has a higher conductivity and hence a higher concentration of ions in solution. And the one with the higher concentration of ions in solution is obviously the stronger base. So first off, I'm just going to rinse off my conductivity sensor to make sure it's nice and clean. And I'm going to come over to my computer and turn the recording on. So we can see at the moment very low conductivity. There isn't anything for it to conduct through, but if we add it to our first solution, our ammonia, and we give it a second, we can see we've got a bit more conductivity. Still relatively low, but let's compare it to our sodium hydroxide. We're going to clean it again in between. What we should be seeing when we get to our sodium hydroxide, we know that that is a strong base, and so we should see a much higher conductivity. Right, let's add it in. And we can see now that our reading is a lot higher. It's now 1,000, whereas before it was 167 odd. So it's definitely stronger base conducts a lot better. The last definition we're going to talk about today is concentrated versus dilute. We know that concentration is equal to number of moles over volume. And so when we're talking about concentration, if we have something that's very concentrated, we have a large amount of substance in a given volume. With something that is not so concentrated, we have a small amount of it in a given volume. The formal definition says a concentrated acid or base contains a large amount or number of moles of acid or base in proportion to the volume of water. A dilute acid or base contains a small amount or number of moles of acid or base in proportion to the volume of water. Let's have a look at a little demonstration to show this. Right, so what is concentrated versus dilute? Often gets a little bit confusing when we think of chemicals, but we all love to have a glass of juice at home. And so if we take a little bit of Oros, this is concentrated, and we pour it nice and new. We can pour a little bit in to our test tube. Right, that's just concentrated Oros. Whereas if I go and I add a bit of water, so concentration, we can see, has to do with the amount of substance in a given volume of water. So we can see that the one on the right here, very concentrated, we didn't add any water. And then this one's sort of a medium concentration, and the one on the left quite dilute when we had a small amount of Oros in the volume of water. So we can therefore see that concentration has to do with the amount of substance or the number of moles of substance in a given volume. That brings us to the end of Acids and Bases Part 1. We look forward to seeing you for Acids and Bases Part 2.